we'll take a look at a small example. And this example is based on an application that is deployed on two systems. There's an application server and there is a database server. The database server has its data stored on an external storage area network with a RAID 0 configuration. You may or may not have talked about RAID levels in either an operating systems course or a databases course. If you looked over my databases course, we didn't cover it at all. I don't think it's that interesting. I think this is one of those, if you read the Wikipedia article and spend 15 minutes looking at it, you'll know enough about it. But if that doesn't make any sense to you, that's okay. In a RAID 0 configuration, you say, I want to take these disks and I want to pretend they're one big disk. And also you can get some data faster that way, because if it's spread across different physical disks, and you do a read, you can read from both disks in parallel. The details of what data is stored where is abstracted away from you by the RAID controller, and you get your data faster. However, much higher chance of data loss, because if any one drive in your RAID 0 configuration dies, then they're all gone. You could lose everything. Other RAID levels have higher levels of redundancy. RAID 1 is mirroring, so you're reducing your available storage space in exchange for faster reads, but also more safety in case a drive has an accident. Anyway, you can read about RAID, as I said, on Wikipedia without me needing to hold your hand through it. And the Java program in question does object creation with 15 threads. And the question that we are trying to answer is, what is the performance of measuring? What is the performance for measuring its objects created per second? Okay, so here's what we got. Throughput in objects per second over time, it's wall clock time displayed at the bottom, shows a serious decreasing trend. And with our number of objects created in thousands per second, we can also see a similar decreasing trend. And to use the technical term, not good. So originally our throughput starts out at being about 45 objects per second, and then it's eventually at about 9 within an hour. And as objects are created, we are, at the end of the test, we've got about 45,000 objects created, and that's not the trend that you want to see. If you need, for some reason, to create 500,000 objects or 5 million objects, things would get a lot worse. So we have to figure out what's going wrong and why. To quote from Sherlock Holmes, this is the Jeremy Brett interpretation of Sherlock Holmes, which has a certain late 80s-ish charm to it. I confess I rather prefer it to the BBC Sherlock version, if only because this one was truer to the original and has fewer flights of fancy, where Sherlock just magically, with no data, comes up with the correct answer. The quotation from A Scandal in Bohemia, which incidentally is the first episode of the Jeremy Brett Jeremy Brett series even, is, "It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts." And that is definitely the case. If we start with a theory, we will probably, just through confirmation bias and our natural tendencies to want to be correct, conscious or otherwise, we'll find ourselves looking for evidence that proves us correct and finding ways to dismiss evidence that is not consistent with the theory that we have thought of. So the first thing we should do is gather data, collect some evidence, don't reach any conclusions. At a high level, here are 4 things that we want to examine: CPU, memory, disk, network. They're not in any specific order, and these are categories rather than specific clauses. This is not Clue, the CPU did it with the lead pipe in the library. I mean, that would be entertaining, I guess. But they are starting points for further investigation, and I put them in a numerical order, and they are coincidentally the numerical order that we are going to talk about today. But there's no reason why you have to investigate them in the order that they're listed here. We just got to do it in some order, so here we have it. CPU. Okay, the CPU is probably the easiest of these things to diagnose. You could look easily using one of the tools, Task Manager, Activity Monitor, as it's called in macOS, HTOP in your Linux machine, and it gives you a little column, and you can see where is my CPU time going, and you can see what's actually happening. You can see, is the CPU maxed out? If it is, that's a good hint that that is our limiting factor. That tells you about right now, but you could look at the long-term average. Checking with a little PC I used to have in my office, Loki, that has since ascended to Valhalla. It ceased to work in about 2016. It's been... the time at which I took this was apparently 7:28 in the morning. At that point, it had been up for 151 days and 23 hours and 38 minutes. 8 users, load average 0.87, 0.92, 0.91. Those last three numbers are the 1 minute, 5 minute, and 15 minute averages of CPU load, respectively. So the 1 minute average has been 87%, the 5 minute 92%, and the 15 minute 91%. I was using at the time CPU cycles to World Community Grid, because I'm single-handedly saving the world, don't you know? But lower numbers mean less CPU usage and a less busy machine, which is usually a sign that we're not maxing out the CPU and it's not our limiting factor. As for why this Linux machine had an uptime of a mere 152 days, it's because I had to shut down the machine and move it a few months before that because I moved offices. I at one time had an office in DC and it was moved to EIT, which absolutely ruined the uptime of that machine, let me tell you. Okay. Let me give you a little more context about interpreting those load numbers, though. So, picture a single core of a CPU as a lane of traffic, and you are a bridge operator, so you need to monitor how many cars are waiting to cross the bridge. Obviously, for safety reasons, you can't allow an unlimited amount of vehicles on the bridge at the same time. If no cars are waiting, traffic is good, drivers are happy. Wasn't there a political scandal about this, about closing bridge lanes or something? Maybe it's better if I stay away from that. If there's a backup of cars, there are delays. People are unhappy. You live in Toronto, or New York, or any other city with a serious traffic problem. These things happen. You are sad. Okay, so if your single CPU load looks like 0.00, as reported by TOP or HTOP, it means there's no traffic. No cars, nobody's using it, nothing's using the CPU right now. And anything between 0.00 and 0.99 means we are below capacity, and there will be no delay. If a new task shows up right now and wants to run, and CPU usage is, 0.5, no problem. CPU usage goes up to 0.6. There's no delay. We're not maxing out the CPU. There's no problem. 1.00 means we are exactly at capacity. If one more vehicle or one more task shows up, then there will be a delay. Somebody will have to wait. Anything above 1.00 means there is a backup, and that means accordingly people have to wait. If load is reported as 2.00, the bridge is full, and there's an equal number of cars waiting to get on that bridge. Or if you wanted it in a car analogy, where if each car here is of load 0.1, with a load of 1.00, the bridge is completely full, couldn't squeeze any more cars in if you wanted. A load of 0.5 means about half of it is being used, and 1.70 means that we have the bridge is full, and there's also some tasks that are waiting. So the thing is that being at or above 1.0 isn't necessarily bad as long as it's temporary. Right, at any given moment, there might be a particularly busy moment where a lot of CPU is requested, and that's okay. You don't have to panic if you ever see it above 1.00, as long as it's not consistently that way. If it is consistently that way, then you start to be concerned because it means the capacity that we have is perhaps insufficient. If you are less than 1.0 but you're getting close to it, then you know how much room you have to scale things up. If we are pretty consistently at 80%, you can say, well, we're at 80% of capacity here, and this is, this will be a problem once we reach 100, but we have a little bit of room to grow. Anything above 70%, it's time to investigate. This could mean that we need to make some changes in our program. It could mean that we need to expand the capacity, buy a better server, something like that. We'll have to investigate. And if we are above 1.0 consistently, that is in fact a significant problem. It means a lot of users are unhappy. We're spending a lot of time waiting. And so the hardware that we have is not adequate to the workload that's being given. If you're seeing something like 5.00 for CPU usage, you should probably consider that to be a red alert situation, because demand so vastly outstrips supply that it's providing a bad experience to people who are using it. Now that's for a single CPU. If you have a load of 3.00 and a quad-core CPU, then we're still okay. There's still more capacity. Just think of that as being 4 lanes of traffic, and if you put all the cars together, it's as if 3 lanes are being used to capacity right now. It won't be exactly like that because you wouldn't have one CPU sitting idle and 3 of them maxed out, hopefully. But just to give you an idea of how are we doing with regard to capacity, this gives you some way of measuring it. Okay, so with an understanding of how to measure CPU usage, in the scenario that we were looking at, what happened? Is it CPU? Well, the application server CPU usage was on average about 10%, and the database server CPU usage was on average about 36%. So probably that's not the cause, right? If CPU were holding us back, we would see that probably one of these two things was at or close to 100%, meaning that the CPU is the slow part. We want to use it more than it is available, and we therefore have to wait. We're not seeing that here. So let's look at memory. Okay. Looking at memory, how could you do that? Well, actually, one shortcut for that is looking at disk utilization. Why? If there's not enough RAM in the machine, there will be swapping and performance goes out the window because the scalability is absolutely ruined by, unfortunately, having to swap unnecessarily. So that's one way to check it. That's the worst case. You can ask via top, incidentally, about how much swap memory is being used, but that's not necessarily interesting. Your computer could keep a lot of stuff around in swap for no reason or for a limited reason, and you shouldn't read into that anything is necessarily wrong. So looking at something like this is again from Loki. It had 8 gigabytes of RAM in it, and of which about 6 3/4 gigabytes were in use, and 1 and a bit are free, and swap was about of equal size, and so on and so on. Okay. The important thing to note is that memory being full isn't necessarily bad in the way that like CPU being at full utilization is a sign of a problem, because it just means the resource is being used to store some stuff. There's no benefit to keeping a huge amount of memory open for a just-in-case kind of reason or for no reason at all. Memory is, in that sense, not as limited, right? We can just keep some stuff in memory, and if we need it, great, it's already there. If we don't need it, we can replace it with something we do need, and we're not losing anything by having it there. The analogy added here is that it's the same with like stockpiling late days. You don't get anything if you stockpile all your late days in the term and you end the term with unused late days. I mean, I'm a big offender in this regard of like having saved up all my late days and never using them in the term, mostly because like, well, I don't know, maybe something will come up in the next assignment, and if I don't need them now, it's better if I save them. And then it's the last assignment, and it's like, well, I'll just submit it because I'm done anyway. And that's fine, but there's no benefit to stockpiling them. There's no bonus for not using them. Sometimes people ask that on Piazza. They're like, so I didn't use all my late days. Can I get a bonus for not using them? And then I have to tell them, well, no, because that's the same thing as putting a penalty on using them, and that defeats the purpose of late days. So, yeah, in this regard, just keep in mind that memory is unlike CPU. If there's nothing for the CPU to do, it goes into a low-power state, idles a bit, which is potentially beneficial if you are looking at reducing your power bill, or this is a mobile device, in which case reducing your CPU usage improves the battery runtime. But for memory, it doesn't matter. Just keep some stuff in there. It's not like going under budget for the year. Memory doesn't forget data if it doesn't happen to be needed right now. So going on about memory appearing full is kind of like getting upset about how system idle process is really hammering your CPU. No, it isn't. And an actual tech journalist actually wrote that, and I will probably name and shame that individual, John Dvorak, from now until the end of time. Surely he feels silly by now. Probably not. Okay, you can also ask about page faults. And the Unix command for this is ps-eo, and then the columns that you're interested in are minor faults and major faults, and cmd, which also tells you some more about the process. Major page faults are we had to go fetch it from disk. Minor is we copied a page from another process. The output of that is really big, so I didn't put it in the notes. But this is because it gives like process lifetime data. So it gives you a huge amount of information, way more than you could ever possibly need. And we can take a look. And we'll see, of course, this is way more data than we could ever possibly need. And for some of these things, we can see somebody running Valgrind something or other here, and there's been 42,472 page faults and stuff like that. This is lifetime, though. So you could have a lot of page faults at the beginning of your program and then nothing for a very long time. And if that is the case, then this information is maybe not that helpful. What you might actually want instead is a report on swapping. And the report on swapping is retrieved by doing vmstat5, and it tells you, based on your process and what have you, about which things are doing swaps. And the swap in and swap out columns are the one to watch for. Unfortunately, in this example, they're not super well aligned, but it's this SI and SO fields here. And they tell you about how much swapping is actually going on. In this example, they're mostly 0, but that's good. You don't want there to be a lot of swapping. This is the slow step if that's what we find. There's a lot of swapping. We're fortunate in this case to see that in our current system, the ECE Tesla system, that's not happening, so no complaints there. If we saw a big number, we would be a bit more upset by that. Keep in mind also, it does have to be a significant number. If you saw just a little bit of swapping, that could be inevitable. Given a sufficiently large problem, it won't be able to all necessarily stay in memory all at the same time, and you would have a little bit of swapping, but a little bit is painful, but not fatal. A lot of swapping is a big concern. Here's, just for the sake of comparison, a swapping report with actual swapping in it. You can see the swap in and swap out numbers there, which should be a bit more concerning if that's something that you see. Okay, looking at disk might seem slightly redundant if memory is not the limiting factor, because you say, well, what if we're swapping? On the other hand, sometimes disk is actually the bottleneck. If we are trying to read a lot of data from disk, we have a file that's stored on disk, and we're trying to send it over the network or something, disk could be our limiting factor. And this might actually be interesting to us. Same also is true if it's a database system. The database may be limited by its disk in terms of doing whatever operations you've asked it for. Well, here's how I look it up for, again, the Loki machine, which is IOStat, where I specify a particular device, and SDA is the one hard drive that was in there. It was not anything special. It was, as far as I can tell, or at least as I can remember, a magnetic drive. And the last column, percentage utilization, there tells you what you want to know. If that is really high, that's a problem. It is, so disk is being maxed out, and that's why things are taking as long as they take. This doesn't tell you quite as much information as we would normally like. You could, if you have root privileges, use IOTop, which gives you a better overview of where the IO stuff is going, but we don't have that option at present. We can also ask about the network with mload. Mload will even draw you a little graph that will tell you about what you need to see. But you can see there is a summary, and 3.32 kilobit per second, the average of 2.95 kilobit per second. So again, like Loki here is really not doing a lot with the network, although over its lifetime, it's actually transferred a fair amount of data. Downloaded the packages to install updates and stuff like that, so the total amount of data transferred is somewhat large. And mload is not as much fun if nothing is happening. You just see like an empty field where a graph would be, but that's the way it's played. Okay, so we got a little bit away from the original question, and the original question had to do with why is object generation slow. It's linked in the notes, the book that this comes from. It's maybe interesting to you if you wanted to dig into the specifics about Oracle 10G and SQL query syntax. But basically, if we looked at it, 96.4% of the total database call time was attributed to database CPU. We said earlier that actually database CPU wasn't the limiting factor, but we didn't consider what was available on the database at all. If we were maxing out one of the 4 cores, then we would see actually, hey, there's a lot of database usage if we looked at one core at a time. If we didn't look at it one core at a time, we would say, well, on average, it's not that busy. So we do have to check carefully our assumptions, so to speak. In any case, you can ask most database servers for a top 5 query where you say, what are the queries that take the longest time? And it is, well, select document ID, class ID, data group ID, consistency ID from object table where object ID equals, and then some value. And why is the performance of this not good? Again, if you took a database course, you will, I'm sure, have come up with an answer. I mean, we are doing a lot of reads from the database. The reads don't necessarily go to disk because there are caches and buffers and what have you, but what's actually missing is we need an index. This is one of the strategies that we've talked about before. Be prepared. If we know an operation is going to query based on some column, something like where object ID equals value, we can put an index on that. Again, if you took a databases course, I'm sure you covered how an index works and what is its purpose. And if you did, then you will understand, of course, why this is valuable and what is important. And basically, however, in terms of programming for performance, it is some additional work is done to prepare the index when it's created in the first place, and then maintain it whenever data in the table is modified, but it makes the query a lot faster when it's time to do it. If you have a book and the book has, an index of, you're looking for all of the times where, I don't know, the word water was used. If no index has been prepared in advance, you have to crawl through the whole text of the book and notice every time the word water is used. If, however, there is that kind of index at the back of the book, you can just look at it and you can flip to the part where it says W and you choose water and it tells you it's located on pages 1, 2, 7, 99, 312. And you've got exactly what you need. It would make it a lot faster to produce any paragraphs that include the word water. And sure enough, we can see that by looking at this, we will find the correct result and find it faster. And so if we don't add the correct index, we can see performance degrades pretty badly with the time, but also creation of objects. And if we do add such an index, then performance remains pretty consistent. which makes a certain amount of sense. As the table gets bigger, it becomes slower to search it if you have to search through all of it. So it makes sense that we would see performance degradation in that respect. And ultimately, it's better if we have the index, because it means that taking a look through the table doesn't take quite as long, even as it gets bigger. So with this in mind, as I said, this is kind of a transitional topic to the idea of scaling things up. We'll take a look in upcoming topics some more at the goal of getting from 1 user to 100 to 1 million to 10 million. I maybe skipped some steps there. Probably you don't go from 100 users to 1 million users all in one jump, but you never know. And ultimately, the idea of figuring out what are your limiting factors will be helpful in the question of, well, what servers, what hardware, what equipment do I need to actually serve the customers that we have.